Hello, hello, I am Mrs. Edwards and we are back. It is time to do math and I love it. Today we get to talk about the inverse function slope relationship. And I've written here at the top the actual theorem, and it's a mouthful, so you can pause it, write it down, and kind of try to digest it, but I'm going to jump to explaining what the heck all that means. I think it's good to start with, when are you going to ever use this relationship? So what ends up happening is ultimately you would like to find the derivative of some inverse function and evaluate it at an x value. The problem is you don't know the equation of the inverse function. If you did know the equation of the inverse function, well, then you could take its derivative and substitute in that x value. You might be thinking, well, I would just go ahead and find the inverse function. But you will know the equation of f of x, or at least some points on f of x, but you can't find the equation of its inverse. If you remember back in pre-calculus, to find the inverse function, you start with your equation. Every x you replace with a y, every y you replace with an x, and then you solve for y, and voila, you have your inverse function. However, sometimes solving for this inverse function is really difficult, if not impossible. Okay, so main idea so far is you do not have the equation of the inverse function, and finding the equation of the inverse function is either difficult or impossible. All right, so let's take a look at the meaning graphically of this relationship. Let's start with a random function. I'm going to call this function f of x. If we wanted to graph the inverse of f of x, right, the inverse is just a reflection across the y equals x line. So that right there would be a picture of f inverse. Now, if I have a point on f of x, and I'm just randomly picking a point on f of x, and I'm going to call that point a comma b. Well, an inverse function, all the x's and y's switch. So if this coordinate here on f of x is a comma b, if I reflect it across that y equals x line, that coordinate that's on the inverse would be b comma a. We would like to find the, if we look here, f inverse derivative at b. In other words, we're trying to find the slope of the tangent to this f inverse function at that x value. But since I don't know this equation, let's look graphically at the relationship at the point that it came from. Okay, but the slope of that light gray line right there, that would be the derivative evaluated at b. Now right there at a comma b, the slope of the tangent to f of x at a comma b, that would be known as f prime of a, right? The slope of that purple one. So what's the relationship between the slope of that light purple line and the slope of the light gray line? Well, let's say that the slope of the purple one, I'm just making it up here, let's say that the slope was 3 over 2. So I'm on the light purple one. I'd rise 3, run 2, and I'd get to another point. Well, if the slope of the light purple one was 3 over 2, well, then the slope of the light gray one would be 2 over 3. Up here in the formula, 1 over f prime of a simply means when you take 1 divided by something, it takes the reciprocal of it. So we're saying that the slope of the tangent at a comma b and the slope of the tangent at b comma a, they are just reciprocals to one another. So we will do a full example here in a moment, But before we get to that example, I want to talk process for just a minute. When you are given that f is differentiable, remember back some of the theorems we've had before, intermediate value theorem, squeeze theorem. The prerequisite to use a theorem is that the function is differentiable. So just those words alone tell us we're going to be using a theorem. Okay, next, we're looking for a little extra information that's going to also guide us to which theorem is it that we're going to be using. And that given information is that the functions are inverses of one another. When you are on the AP exam, you don't have a lot of time. So there has to be some things like you see it, you do it, and you don't even think too much about it. So if you see that two functions are inverses of one another, immediately you know this is the theorem that you're going to be using. Okay, now if you're going to use this theorem, then what's next? Okay, well, if they're inverses, let's just talk big picture for a second. That if you have a point a comma b on the original function, then the inverse has the coordinate b comma a. Everything about inverse functions is really about the fact that x and y, they switched places. So if we want to know f inverse's derivative at b, it's reliant on at 1 over f prime of a. Now, what does that mean really quick? F prime of a, 1 over. Whenever you take 1 and divide it by something, it just spits out the reciprocal. Like 1 divided by 2/3 is 3 over 2. Okay, so this is really saying the reciprocal of f prime of a. So we want to find f prime of a. That's our goal. But before we can find f prime of a, we need to know what a is. After you know a, then you can find the derivative of f and plug it in. But first thing, we need that full coordinate. Okay, we've got to find that original a comma b. We have half of it because if you are being asked to find f inverse's derivative at b, the b there is the x on the inverse function. So it is the y coordinate of the original function. If you know the y coordinate of the original function, you can then use that to figure out the x coordinate that goes with it. Okay, so we're going to use the fact that b is the y coordinate of f of x to figure out what the x coordinate is that goes with it, the a. Okay, once you figure out what a is, well then you can find the derivative of f, plug in a, and you have f prime of a, and then lastly, you just flip that answer over, and you now have 1 over f prime of a. It's a bit of a mouthful, but the big takeaway here is the fact that you were given that the function's differentiable. I know I need to use a theorem. Then I'm given that two functions are inverses. I know I'm going to use this inverse function slope relationship. Step 1 is to figure out what is the full coordinate, a comma b, because only until you know what the a comma b is, then you're going to be able to figure out what f prime of a is and flip it over. Okay, let's take a look at an example. Here we have a function f of x, and we want to find f inverse's derivative at 3. Now you may start thinking, well, f inverse, I'm going to go back to my original function f of x, and every place I see a y, I'll make it an x. Every x, I'll make it a y, and I'll solve for y. Then I'll just have the equation for f inverse, and I can take its derivative. Well, let's just think that through a little more. F of x would become, that's the y, so it would turn into x. And each one of these x's, x to the 5th, 2x to the 3rd, etc., all of those x's would become y. we would have the equation x equals y to the fifth plus 2y to the third plus y minus 1. Now we need to solve for y, and if we could solve for y, that would be the inverse function. We can't solve. Okay, so this is why we need this theorem. We cannot find f inverse. If we could, we'd find it, take its derivative, and plug in 3. So next thing we need to do, realizing we need this theorem, is we need to figure out the coordinate. Okay, so 3 is the x coordinate on the inverse function, which means it is the y coordinate on the original function. So far, we know that f inverse has the point 3 comma something, and the f function has the coordinate something comma 3. We need to figure out a. We don't know anything about f inverse, so if we want to figure out a, the only thing we can do is go to f of x. And since we know the y coordinate is 3, I'm just simply going to replace the y with 3 and use it to find the x coordinate, which is our a. Okay, now I want to solve this equation. You can use your graphing calculator in this instance to solve. And if you solve any equation, right, first step, good idea to move everything to one side equal to 0. So I subtracted 3 over. If you were not going to use your graphing calculator, flashbacks to pre-calculus, you would need to use the method P over Q to find the potential zeros and then ultimately use those to factor. But we're not going to do all of that work. We're going to grab our graphing calculator to solve this equation. So when you grab your graphing calculator, you're going to enter in the x to the fifth plus 2x cubed plus x minus 4 in for your y. I'm just checking here my window to make sure it's big enough to hold this function. I graph it, and wherever it crosses the x-axis, that is the answer. So I'm using the 0 feature. I'm going to put that little blinky dot to the left of where it's crossing the x-axis and arrow over to the right of where it's crossing. Enter, enter, and I end up with the x-intercept is located at 1. Okay, so the solution to this fifth degree, x to the fifth plus 2x to the third plus x minus 4 equals 0, the answer there is 1. Okay, I now know A. Okay, A is 1. Now, I also know if f is 1 comma 3, then f inverse is 3 comma 1. But frankly, I don't really need to know that. I just need to know what the A value is in the f function, because our answer, remember, is going to be 1 over f prime of A. So that's why I need to know that A. Now that I know what A is, I need to find 1 over f prime of A. So next I need to find the derivative of f and then plug in A. Well, finding the derivative of f, that's pretty straightforward. Okay, I just use the power rule, derivative of x to the fifth, 5x to the fourth. Derivative of 2x to the third is 6x squared. Derivative of x is 1. Derivative of minus 1 is 0. Okay, I'm going to substitute in 1. And I now know the answer to f prime of A is 12. But the answer to f inverse's derivative at B is the reciprocal of f prime of A. So what's the reciprocal of f prime of 1? The reciprocal of 12 is 1/12. Whew! Okay, so a lot of pieces going everywhere. Quick recap. You were given that you had two functions you were working with that were inverses. So immediately you think of this relationship right here. To be able to use this relationship, you need the full coordinate a comma b. And so f inverse of 3, it means that this is the x value on the inverse function, so it is the y value on the original function. Then you use the fact that this 3 is the y value on the original function to figure out what the x value is on the original function when the y is 3. Now that you know a, you can find the derivative of f and evaluate it at that number, and then flip it over. Okay, sometimes you're going to be given a table instead of a function. Maybe you're lucky and they just hand you a comma b. If they hand you a comma b, you're in great shape. Or maybe they give you the coordinate on the inverse and you change that around so you know the original point on f. But your focus is on finding a, and once you find a, you find the derivative of f at a and flip it over. Okay, you might even pause the video, like rewind just a little bit here, pause the video at the beginning of this example so that you can kind of walk through the steps as you're doing each problem so you don't lose your place, and then maybe you'll get the hang of it. You do a few more and then you could do it on your own. Okay, all right, good luck.